Hi everyone, this is coming to you from Education for All. We are starting to solve problems under infinitesimal calculus. We have arrived to a point wherein we have to consider the limit of a function, for example. We derive this formula here from the previous video. There are sets of 4 videos you got to watch before you start to looking at problem solving. Because if you don't watch those videos, although you might be able to solve problems on your own, get them correct, but you might not understand the principle behind what you are doing. This conclusion you see here, m is equals to the limit as h tends to 0, f into x plus h minus f of x divided by h is what is called the fundamental principle of calculus. This one here, this m means gradient, simply means gradient. And what that means is steepness. You have something like this, and you have a line, a function like this, you can call it f of x, y equals f of x. So if you take any 2 points here, you want to see the steepness of this function. Yeah, you can just take 2 points here, then you project them on the x-axis, bring this one here, you are now looking at the distance from here to here and the distance from here to here. So this gives you the gradient, which we normally represent by the letter m, and this is same as the rise all over run. The rise simply means this distance from here to here. The distance on the y-axis is the rise, and the distance, the displacement on the x-axis is the run. So this is what they have done here to arrive at this function you see, or this relationship you see here. M, which is the gradient, is equal to the limit as h tends to 0. This is the h. As this h keeps on reducing, it will not reach x, but it will approach x. It will come very close to x. That is when you are starting to reduce this gradient, yeah? Then this function holds. You know how I arrived here. That's why it's good to watch the 4 previous videos, and you know why this is important in calculus, because it's from this principle you see here that calculus is born. This principle, the fundamental principle of calculus. Now we are given a problem to look at. The problem says f of x equals x squared. You know, it's like saying y equals x squared. And of course, if you have covered quadratic equations, you know what this function will look like. This function will look like this. Yeah, it's a parabola with a minimum turning point. This function will look like this, y equals to x squared. It will look like this, right? So now they say show that f prime x is equals to the limit as h tends to 0 2x plus h. Show that f prime x is equals to this, and hence deduce that f of x equals to 2x. We follow this principle here. This f prime x gradient of a function gradient is also sometimes represented by m, and it's also f prime of the function f prime. This prime, same as this, same as gradient. So that's what they mean here. It means this m, right? Just different way of representing gradients of a function. Right. So now let's see what we have here. Applying this first principle of calculus. We know already f of x is equals to x squared, right? And then f prime x would be what? This would be, you have x squared. It will be x plus h following this. It will be the limit f x plus h, but the x has squared, so it means we need to square this, minus f of x and f of x minus f of x. Anyway, let's put it for now, f of x. The limit as h tends to 0 all over h. So this is what we get, right? So this will lead us to f of x is equals to the limit. We just need now to expand here and do something. The limit as h tends to 0. So this will give us now x plus h all squared minus x squared, because f of x is x squared, and f of x plus h will have x plus h squared, right? This one here, all over h. We want to show that f of x, f prime x is equals to this. So now let's carry on. If you expand this, let's expand x plus h squared. This will give you x squared plus 2hx plus h squared. When you expand this, this is what you get. Then you have minus x squared here. Yeah, so this is what we'll get at the top. But the x squared, this is plus x squared minus x squared. So these two will cancel. So what remains is 2hx plus h squared at the top. Yeah, 2hx plus x squared. That's what is left at the top. So now, still have it here. The limit as h tends to 0, you are having 2hx plus h squared. Now we have our h at the bottom. So what else can we do here? What else can we do? We can factorize h. You can factorize h squared, h here. You can factorize it. So you'll now have the limit as h tends to 0. You will have h into 2x plus 1h all over h. When you factorize, this is what you get. Let me bring this one further here. Too far. Still a little bit. Correct. Yeah. So we can see that we can cancel the h. This h will cancel this h. So we'll now have the limit as h tends to 0, 2x plus h. But as h tends to 0, this becomes 0. That's what this is saying. When h is very, very, very small, so you tend to ignore it because it's going towards 0. The number is reducing. It's going towards 0, so it becomes negligible. So in that case, you will have the limit as h tends to 0. This will tend to 0 now. So you'll just have 2x. That is, this is the first part here, as h tends to 0. This is the first part. This now is the b part. Hence, deduce that as f of x tends to 2x. That is when h tends to 0. This will become, this is the b part here. The a part stops here. This is the a part. We've proven this. 2x plus h. So the b part hence deduce that f of x is equals to 2x plus 2x. That is when this h is approaching to 0. This number keeps reducing. Say it is 1. It's going to 0.99, 0.5, 0.04, 0.01. So it's going towards 0. That is what this means. So if it's going towards 0, you better ignore it. And then what is left here in the function is 2x. So thank you for watching this video. Bye-bye.